Welcome to the Deep Dive. We're the show that pulls out the key insights from complex topics, basically giving you a shortcut to getting up to speed. Today, we're getting into something I bet many of you have run into. That moment of frustration, right? You ask a large language model what seems like a simple, factual question, and it answers super confidently, but it's just completely wrong. I mean, I've seen it myself. It's kind of baffling. Like, picture asking a top AI, what's Adam Talon Kalai's birthday? Only answer if you actually know. And then it just spits out 3 different wrong dates. 0307, then 1506, then 0101. The real answer is apparently sometime in autumn.
Right. Miles off.
Exactly. Or that DeepSeek example that went viral. You ask how many Ds are in DeepSeek, simple counting, and it confidently says 2 or 3, sometimes even 6 or 7. Anyone can see there's just one D. It shakes your trust, doesn't it?
It absolutely does.
So our mission today is to explore why language models hallucinate. We want to cut through the noise. This isn't really about some, mysterious AI ghost in the machine. It's more about, a mix of how they're trained statistically and maybe some unintended side effects of how we test them.
That's a great way to put it.
We're aiming to give you a clear understanding of this really critical challenge in AI, drawing straight from the latest research. Okay, so let's start with the basics then. We hear this word hallucination thrown around a lot with AI. What exactly do we mean by that? And maybe more importantly, why is it different from just, a regular error? Why is it such a big deal?
Yeah, that's a key point because AI hallucination isn't like the human experience at all. We're not talking about the AI like seeing pink elephants. Instead, it's about generating these overconfident, plausible falsehoods. That's the crucial part. They sound right, they look convincing, but they're just made up.
Plausible falsehoods.
And that, as you said, it hits right at the core of utility and trust. If you can't trust the output, what's the point? Take those examples you mentioned. Adam Talon Kalai's birthday. The model was specifically told only if known.
Right. Don't guess.
Exactly. And yet, it confidently fires off 3 wrong answers. And it's not just birthdays. Other big models, ChatGPT, DeepSeek, Llama, they've all confidently given wrong dissertation titles for him. Wrong years, wrong universities, too. Like ChatGPT said it was boosting online algorithms and other topics from CMU in 2002. DeepSeek claimed algebraic methods at Harvard 2005. Llama, efficient algorithms at MIT 2007.
Wow. All completely wrong.
All completely wrong. His actual dissertation was probabilistic and online methods in machine learning, CMU 2001, so they weren't even close, but they sounded specific and authoritative. And then that counting task, how many Ds in DeepSeek? DeepSeek v3 kept saying 2 or 3. O's went even higher. These aren't just little mistakes. They're confident fabrications about stuff that's, easy to check or even right there in the prompt itself.
That really does hammer home the issue, doesn't it? I mean, if it gets basic facts wrong or can't count letters in its own name, how can we rely on it for, complex analysis or critical information?
Precisely.
It's not just a minor bug. It makes you question the whole system's reliability. Okay, so we know what they are, these plausible falsehoods, and why they're a problem, but where do they actually come from? My first guess, and probably yours too if you're listening, is maybe bad training data, garbage in, garbage out. But I get the feeling it's deeper than that, more fundamental. What's the real story here?
Yeah, you're right to push past that initial thought. It's easy to blame the data, but the really interesting insight from the research is that these hallucinations often start simply as errors in binary classification.
Yeah, binary classification, yes-no question. How does that relate?
Well, think of it less like the AI is trying to be deceitful and more like it's making a statistical prediction that happens to be wrong, but it outputs it with high confidence anyway. Imagine the model is constantly, implicitly asking itself for every potential word or phrase. Is this a valid, plausible continuation based on everything I've learned? It's solving what researchers call the is it valid or the V problem.
Okay, is this valid? Not necessarily is this true.
Yeah, exactly. It's about statistical coherence based on its training data patterns, not necessarily factual accuracy in the real world. It's like a student facing a super hard exam.
Right.
When they're unsure, what do? Sometimes they guess, right? They write something that sounds plausible, hoping for partial credit, instead of just writing, I don't know.
Yeah.
The LLM is kind of doing the same thing statistically. And here's the really surprising bit. The research suggests that even if you had perfectly clean, error-free training data, the way these models are optimized during pre-training would still lead them to make errors sometimes.
Wait, really?
Yeah.
Even with perfect data?
Yeah. It's not just about data quality. It's baked into the statistical objectives, the very process of learning to generate language probabilistically. There's this inherent pressure.
Wow, okay. That's a big idea. So errors are kind of inevitable, statistically speaking. What are the main statistical factors then during pre-training that cause these errors?
The research points to a few key factors for the base models before any fine-tuning. First up is what they call arbitrary fact hallucinations.
Arbitrary facts, like the birthday example.
Exactly like the birthday. These are facts where there's no succinct pattern. There's no rule or logic the model can learn to figure out Adam Kalai's birthday. It's just a specific arbitrary piece of data. This leads to what's called epistemic uncertainty. Basically, the model just doesn't know for sure because the fact doesn't fit a generalizable pattern it's seen repeatedly.
Makes sense.
And there's a fascinating concept here related to Alan Turing's work, actually. It's called the singleton rate. Think about how many facts in the training data appear only once.
Singletons.
Right. So Turing's missing mass estimator helps predict the probability of things you haven't seen based on things you've seen only once. Applied here, if maybe 20% of birthday facts are singletons in the training data, then you'd expect the base model to basically hallucinate on at least 20% of those facts when asked, because it only saw them once. It doesn't have strong statistical evidence, so it's likely to guess when prompted. It's fundamentally uncertain.
So the less frequently a specific fact appears, the more likely the model is to just make something up.
Pretty much, yeah. Especially for these arbitrary one-off facts. The second factor is simply having poor models.
Poor models. You mean the AI architecture itself?
Exactly. Sometimes the model's structure or its size or its design just isn't well suited for the task you're giving it. It cannot represent the concept well. Remember the how many Ds in DeepSeek example. DeepSeek R1, which is built more for reasoning, does much better than DeepSeek V3. That suggests it wasn't just the data. The V3 model itself was maybe a poor model for that specific simple counting task. It's like, older language models, trigram models that only look at the previous two words.
Yeah, they often produce nonsense sentences.
Right, because their architecture was too limited to grasp complex grammar. The model itself wasn't up to the job. Same idea here, just more sophisticated. And there are a few others worth mentioning briefly. There's computational hardness. Some problems are just incredibly difficult to solve, even for AI, like complex decryption. There's distribution shift. This is a big one. The model sees prompts that are different from its training data out of distribution and makes mistakes. Real-world questions are often slightly out of distribution.
Like asking about a pound of feathers versus a pound of lead, that kind of tricky question.
Could be, yeah. Or just phrasing things in a novel way. And finally, there's the classic GI Go, garbage in, garbage out.
So the bad data does play a role sometimes.
Oh, definitely. If the training data contains factual errors or, conspiracy theories, the model might learn and repeat them. That's still a factor, just not the only factor, or maybe not even the primary one for these confident falsehoods.
Okay, so putting it all together for pre-training, it sounds like these errors, these confident guesses, aren't just bugs to be ironed out. They're almost a natural consequence of the statistical learning process itself, baked right in.
That's a very good summary of the pre-training situation, yeah.
Which brings us to the next big question. If these errors are so fundamental, starting way back in pre-training, why haven't our fancy post-training methods fixed them? Techniques like RLHF reinforcement learning from human feedback, where humans literally guide the model. You'd think that would stamp out the hallucinations, right? But apparently not entirely. And the reason why is, well, you called it a socio-technical problem, which sounds intriguing.
It really is quite fascinating and a bit ironic, actually. The issue isn't necessarily that RLHF can't reduce hallucinations. It's that our current systems for evaluating these models often work against that goal.
How so?
Basically, our evaluation procedures often end up rewarding guessing instead of rewarding honesty about uncertainty.
Rewarding guessing.
Yeah. Let's go back to that student exam analogy. On a multiple choice test, if you're unsure, what's the best strategy if there's no penalty for wrong answers?
You guess. You might get lucky.
Exactly. You maximize your expected score by guessing. And on written exams, students might bluff, right? Write something that sounds plausible even if they know it's shaky.
Sure. Happens all the time.
Well, language models are often evaluated using very similar principles. The most common scoring system is binary. 1 point for correct is 0 points for incorrect. Crucially, that 0 points also applies if the model says, I don't know, or gives no answer.
I see where this is going. There's no downside to guessing and potentially an upside.
Precisely. From the model's perspective, trying something, Even a complete fabrication that sounds specific and confident, like September 30th instead of a vague autumn, is often the statistically optimal strategy to maximize its score on these benchmarks. Let's make it concrete. Imagine model A is perfectly aligned. It always says, I don't know when it's uncertain. It never hallucinates.
Okay, the ideal, honest AI.
Right. Now imagine model B is very similar, but its strategy is, when uncertain, always guess. Always provide a specific, confident-sounding answer, even if it's pulling it out of thin air.
A bluffer AI.
Exactly. Under standard 0-1 scoring, which model gets a higher score on average?
Model B, the bluffer. Because some of its guesses will accidentally be right, and it never gets penalized more for being wrong than for saying IDK.
You got it. Model B will outperform Model A. This creates what the researchers bluntly call an epidemic of penalizing uncertainty. Our tests are implicitly telling models, don't admit you don't know, just guess confidently. And this isn't just theoretical. The research looked at popular, widely used AI evaluations. Things like GPQA, MMLU Pro, SWE Bench, even something called Humanity's Last Exam. The vast majority use this kind of binary grading and offer no IDK credit. Even evaluations like WildBench, which use a more nuanced rubric graded by another AI, can end up scoring a truthful, I don't know, maybe a 3 or 4 out of 10, lower than a response that's partially helpful but contains hallucinations, which might get a 5 or 6.
So even the more sophisticated grading might still push the model to guess rather than admit ignorance.
It inadvertently can, yes.
Yeah.
The incentive structure is subtly but powerfully pushing models toward generating something, anything plausible, rather than expressing their actual limits.
That is kind of mind-blowing, actually. We're trying to build trustworthy AI, but the very yardsticks we use to measure progress are encouraging them to be, well, untrustworthy guessers.
It's a significant challenge. It highlights how the technical problem of hallucination is tangled up with the social or procedural problem of how we evaluate performance.
Okay, so if adding more of the same kinds of tests isn't the answer and might even make things worse, what do we do? How do we fix this evaluation problem to actually encourage honesty?
Well, the argument is that simply layering on more hallucination-specific tests isn't the core solution. The real leverage comes from fixing the incentives in the evaluations we already use. The root problem is the abundance of evaluations that are not aligned with truthfulness under uncertainty.
So change the existing tests, don't just add new ones.
Primarily, yes. The key proposal is to modify the scoring of existing benchmarks by introducing what are called explicit confidence targets.
Explicit confidence targets. Okay, what does that look like in practice?
It means making the scoring rules explicit about confidence. Imagine instructions for an evaluation prompt saying something like, answer only if you are more than, say, 90% confident, T=equal 0.9. Mistakes will be penalized 9 points, T1T, while correct answers get 1 point, and answering I don't know gets 0 points.
So you're introducing a penalty for wrong answers, just like some real-world exams do.
Exactly. And crucially, the penalty is tied to the confidence threshold you set. With this kind of scoring, the model is no longer incentivized to guess wildly. Its best strategy becomes, only answer if my internal probability of being correct is higher than that 90% threshold T. Otherwise say, I don't know, to get 0 points, which is better than the -9 penalty for being wrong.
That makes intuitive sense. It changes the calculation for the model.
It fundamentally shifts the incentive structure. It encourages what the researchers call behavioral calibration. The model learns to output the most useful response it can while staying above the required confidence level.
So instead of just a vague instruction like don't hallucinate, we're giving the AI clear mathematical rules. Be this confident or say you don't know, and the scoring backs it up.
Precisely.
And you're saying this shouldn't just be for some new special honesty test, right? This needs to go into the big mainstream evaluations.
Absolutely. That's critical. These confidence targets need to be incorporated into existing mainstream evaluations. Think about SWE Bench, the one that grades software code patches. Right now, suggesting a buggy patch might not be penalized heavily enough compared to saying, I can't fix this. With explicit confidence targets and appropriate scoring, the model would be incentivized not to provide a potentially harmful incorrect patch unless it was highly confident it was correct.
So apply it where it matters, in the tests that developers are already using to benchmark and improve these models.
Yes. Tackle the problem where the incentives are currently misaligned. By giving models this clear, statistically sound reason to admit uncertainty, we can start to genuinely shift their behavior towards reliability and trustworthiness.
It really makes you think, doesn't it? Imagine interacting with an AI that actually knew its limits and wasn't afraid to say, I don't know, or I'm only 70% sure about this.
It would be transformative.
How much more useful would that be for you personally, whether you're prepping for a big meeting, trying to analyze something complex, or honestly just trying to learn something new online? It changes the game from, maybe this is right, to, okay, I can probably rely on this.
It fosters a much healthier and more productive human-AI collaboration.
Okay, so let's wrap this up and bring it all together. We've really unpacked AI hallucinations today. And the big takeaway seems to be they aren't some mystical AI quirk. They really come down to two main things, right? First, these inherent statistical challenges baked into pre-training dealing with arbitrary facts, limitations of the model architecture itself.
The statistical genesis.
Right. And second, this kind of surprising persistence problem. Our own evaluation systems, the way we test these AIs, have been accidentally rewarding them for confident guessing instead of admitting uncertainty.
Exactly. The pre-training creates the potential for error, and the post-training evaluation system inadvertently encourages those errors to manifest as confident hallucinations.
But the good news is, understanding this points towards the solution.
That's right. The power of incentives here is huge. By fundamentally changing how we score models in existing benchmarks, by using these explicit confidence targets, we can actually change their behavior. We can nudge them towards being more honest, more calibrated, more trustworthy.
It's about building AI that doesn't just know a lot, but also knows what it doesn't know.
That's the goal.
Which leaves us with a final thought for you, the listener, to maybe chew on. If simply tweaking how we measure performance, how we score the tests, can make such a big difference in AI admitting uncertainty, what other subtle biases or maybe undesirable behaviors, not just in AI, but maybe even in our own human systems, our education systems, our workplaces, might we be accidentally encouraging just through the way we measure success? What could behavioral calibration look like beyond AI?
That's a deep question.
Something to think about. Thanks for joining us for this deep dive.